Okay, welcome back to class 10. This is the second video. Previously we were talking about these degrees of freedom and the stiffness matrix, and we're going to talk about that some more. But let's first talk about different element types, right? So there's lots of different element types. Now, SolidWorks simulation might make it deceptive because they really are only using one element type for solid stuff. They do have a shell element. It's not a great one. So you could do a thin-walled thing by representing surfaces with a shell element instead of having this triangular tetrahedron thing. That they can get away with doing that because elements have really come a long way, and the stuff that's underneath the hood, the element formulation, has had lots of little tricks and things over the years. And a company like ANSYS has a lot of elements to offer, lots of elements to choose from. There's probably a few that are kind of like the go-to ones for general stuff, but SolidWorks kind of hides that from you. And basically, you can make, by the way, I should say, you can make stuff in beam elements, right? So you really have three kinds of element types in SolidWorks simulation. You have beam elements, shell elements, and then the basic solid tetrahedron element. But those some of the things that are being hidden from you are there's more than just for their basic element. There's more than just the nodes that you're seeing at the corners of elements. There's actually mid-side nodes. So here's in Shigley where they're describing some of the kind of like this historically thing, right? So the first elements that we might want to do are surface elements. There's also two-dimensional elements that we don't really use too often in SolidWorks, but you can do. And a lot of times it's really smart to make as simple a model as you possibly can get away with. And if you can do it in 2 dimensions instead of 3 dimensions, that's all the better, because you're going to get better results. It's going to be easier to to change things and to interpret the results even, and to see that we're gonna talk about this in a minute. We're gonna talk about convergence here in a second, and that's a really big idea, an important thing in finite element analysis. But you can tell it is good to know that there are different kinds of elements, and these mid-side nodes really do kind of help to solve some of the problems that had been associated with early finite element analysis. And one of the big things that has occurred now is that used to be we always wanted to deal with either squares in 2D or cubes, and as close as a symmetric cube as we could possibly make it, as most a symmetric square as we could make it. That would really help for our solution to the thing. So that's the whole meshing process. I don't know if I used the word mesh, but we want to try to mesh the thing, which is the discretization, right? And that mesh, working on that mesh is a lot of the art of FEA, trying to get that really good. And it used to be a little bit more of an artistic thing because you used to have to make them really square, and trying to figure out how to make something convoluted shape in the thing and always keep everything as cubes could be really challenging. Sometimes you'd have to be kind of clever to do it. But now we could use because the triangle elements were too stiff, was basically the idea. By putting in mid-side nodes, we're able to kind of adapt that. But we still want to be careful when we mesh something, not to get too thin and narrow of a triangle. Right? We want to have as nice and symmetric as we can. We just don't want these weird shaped elements because they will give us bad results. A lot of times it's because they're too stiff. So these mid-side nodes really did help onto things. Now, in right here we have in Shigley, they're not even showing that kind of element as one of the choices, but that is one of the baseline elements, is to have a tetrahedron with mid-side nodes. That is the basic go-to element in SolidWorks simulation. Here's another element. I just figured I'd pull this out of the ANSYS. They have a theory manual, and so here's just a basic beam element. And noteworthy, there are 6 degrees of freedom at each node, right? There's axial, there's left and right, and there's up and down, right? So there's just X, Y, and Z, right? So it can translate in any of the 3 directions, but it can also rotate, right? Because it has bending, right? So it's got a angular degree of freedom at each one. So this is a 12 degree of freedom element. Just one element has 12 degrees of freedom, and you can see there's a lot of zeros inside here. This is some shorthand right in there, so there's a lot more to this in this element. But some of the very first finite element analysis was done with these truss elements, which are really just springs, or these beam elements. And some of the stuff that was originally done for NASA was done with elements that were maybe not quite this complicated, but everything was made out of those trusses to try to represent what the real structure was. It's pretty amazing. All right, so the solution to the FEA requires either, okay, so old school would be to invert this matrix, which is essentially, I'm going to move my head right there, it's out of the way. I mean, this makes it simple right here, right? The equation is F equals K times U, but matrices and column matrices. But we want to find U. In order to do that, we need to invert this and multiply it onto the other side, and then we get our displacements, which we know, like I mentioned, you can find strains, and from strains you can find stress. But now this is really inefficient. So there was all kind. If you take an FEA course, we offer one here at University of Hartford. I suggest it because then it's a more advanced class. Take it as a graduate school class. It really does start to get you a little bit more appreciation for what's going on with the math and what's going on underneath the hood of the computer. But there's a lot in a course like that. They would start to tell you these little schemes, Gaussian elimination, and I think this is lower and upper. I'm trying to remember the terms for these. It's like a way to make the matrix we're just playing with the matrix shape really, and trying to kind of turn it into, instead of a symmetric one, it'll still be symmetric, but you're just playing a little game, and you try to make it so that it's like more of a triangle, and then you can start solving one row after another. It's a means. I think it's quadrature. I think I'm getting that word. Anyway, you will see messages a lot when things aren't solving correctly about some fatal flaw or and give you, there's options to try to get by that when something's not solving correctly, and you get a message, and there's a lot of different options. So there's more to it than just wanting to know why it works the way it does. But sometimes when you're troubleshooting a more complicated situation, because not every situation solves nice and easily for you. You might come up with, and that's actually pretty common, right? Most problems that you're going to want to solve are complex enough that you need to use the computer, and if that's so, there's a good chance that you're going to get these weird situations, and you need to troubleshoot and go backwards and understand what the messages are, and or at least be able to look them up and then understand what the description of them are. And a lot of times it's about trying to do the inversion, but a lot of the solvers take a less direct route. So instead of taking, I'm just trying to hardcore invert that matrix or use some kind of scheme on inverting the matrix, they'll instead do a numerical technique to try to make an estimate, and then they have an error, and then they solve, and then they do a first guess of the thing, and then they check the error, and then they refine the thing, and they go back, and they do a little iterative loop there until they're able to get convergence or within a margin of acceptable error. And that's a lot of computer solutions are now based on various schemes, and with pretty good results. And that combined with those mid-side nodes has really, in addition to computer processing power, that really has sped up solutions. So let's see, another example of convergence, and I think I will end the video after I go through these, is so you might actually want to do your own type of convergence. Now, I think there are some automated things that you can kind of try to have some kind of tolerance and that kind of thing. But there's also you doing a type of convergence, and I might call this a mesh refinement study. And what you can find as with increased degrees of freedom, right, increased mesh density, as you increase the quality of the mesh, you would hopefully start to converge at a solution, right? And so even with just maybe the most basic of FEA studies, you might want to start out with a coarse mesh to make sure that it solves, and then refine the mesh a little at a time, and then to see what the effect of that mesh is. Because you could be wasting a lot of computer power, but you also might have an incident where it doesn't converge, right? So like if you have a very sharp corner in something, you could have a singularity. And so if you have a coarse mesh, or even just a a fairly nice mesh, you might think that's the answer. But if you refine it in the place where there's a really hard notch, you might find that it just keeps going up. So you can't believe the stress that you got in the earlier, less refined mesh, because you have a singularity. And that this is just one example where that might come up. So you have to in order to interpret the results, you really have to be aware of this happening. So just as I just put a little circle on here. I just put a force of like 1 or something on there. And so this is like a coarse mesh, and I refine the mesh. So you could just as a demonstration of mesh refinement, right? So this is a discontinuity, and we'll talk about stress concentrations coming up when we start chapter 5. But this is just this is a stress concentration, and we could actually look up in a book and see what the known expected stress is going to be. But you can see that it's changing, and so here's a more refined mesh and a more refined mesh as we're coming up here, and you can kind of see it's starting to look good, but it's really the actual values that we care. And now I think I started adding something called a localized mesh. I'm trying to think of the name of it now. Let's see, what's the name of these things? I'm trying to think. It's a mesh control, right? So I can apply a mesh control onto this. So let me go back to my thing here. So I applied a mesh control, and so these other ones I just globally said make a smaller element size, and then I said, okay, well no, right here locally, because that's where the stress is high, that's where I would want to like increase the refinement. And I did it some more, and I did it some more, and I did it some more, and then I plotted them out, and I'm just numbering on the bottom my attempts. I didn't. There is ways to like talk about mesh density and that type of thing, or number of degrees of freedom. But I just said here are my attempts, and you can start to see that we start to converge, and that's really the big idea that I wanted to get across, right? That that this thing is sensitive to what the mesh is. But there's a certain point where you don't need to just keep increasing the mesh, and it's just sort of a waste of your time. This one solves pretty easy because it's just a simple problem. But you could see that this happens. So you need to do a little bit of this type of study. You don't want to go crazy with it, and send millions of degrees of freedom for every single problem. But you do want to see have like a little mini study all the time to see like, oh, what is the effect of doing a mesh, especially where there's high stresses in a local area. So there you go. That's my video 2 here, and I made it about the same length. So that's kind of successful. And if you are listening to this video and are a much more knowledgeable FEA person, hopefully you can put a comment down and tell me why I'm wrong, and I don't mind. But thank you.